Georgia, 1968. A sky the color of gunmetal. On the runway at Marietta, something enormous begins to move. At 247 feet, its wings stretched wider than the Wright brothers' first flight was long. For over a decade, it would be the largest aircraft ever built. But somewhere in the design studies, a radical alternative was buried. What if that alternative had won? What if the C-5 Galaxy had been born, not as a tube and wing giant, but as a flying wing? This is the story of the aircraft that carries America's wars, and the forgotten shape that almost carried them instead. Every C-5 that has ever flown owes its existence to a design competition fought in boardrooms, wind tunnels, and the halls of the Pentagon. Before we ask what could have been, we have to understand what truly was. Because the real story is stranger than the speculation. In 1961, American military planners faced a growing problem. The Cold War demanded a way to move heavy equipment anywhere in the world, fast. The existing fleet, the C-13-3 Cargomaster and the newer C-14-1 Starlifter, simply couldn't carry the Army's largest vehicles and helicopters. The Army wanted a jet transport that could haul over 80 tons of cargo, land on rough airstrips, and still cross oceans without refueling. In 1963, the Air Force formalized this need into a program called CX-HLS, the Heavy Logistics System. Boeing, Douglas, General Dynamics, Martin Marietta, and Lockheed all submitted competing designs. Each company believed it held the winning shape. In September 1965, Lockheed's design was chosen, a conventional high-wing, four-engine giant with a T-tail and a cavernous fuselage. But behind closed doors, Lockheed's engineers had also studied a completely different shape, one with no fuselage tube at all. Construction of the real C-5 began in 1966 at Lockheed's sprawling Marietta, Georgia plant. It was, at the time, the largest manufacturing undertaking in aviation history. Thousands of workers building a machine bigger than most buildings. On March 2, 1968, the first C-5 rolled out before 10,000 spectators and President Lyndon Johnson himself. Johnson called it a symbol of American power, a machine that could move an entire Army brigade across the globe in hours, not weeks. But building the real Galaxy meant solving a nightmare of structural engineering, because nothing this large had ever flown before. The C-5's designers chose a high, cantilevered wing to keep the fuselage low to the ground, perfect for drive-on, drive-off cargo loading. 4 General Electric TF-39 turbofans, each producing over 40,000 pounds of thrust, were slung beneath the wings, the first high-bypass engines ever built. The T-tail kept the horizontal stabilizer clear of engine exhaust and rough field debris, a signature silhouette that became instantly recognizable. Every design choice served one goal: carry the most cargo over the longest distance from the roughest runways possible. Yet in the same era, aerodynamicists elsewhere were exploring a competing philosophy: the flying wing. A flying wing carries its payload inside the wing itself, eliminating the heavy fuselage tube and, in theory, cutting drag dramatically. Jack Northrop had chased this dream for decades. His flying wings promised efficiency, but they came with brutal engineering challenges. On June 30, 1968, test pilot Leo Sullivan eased the first C-5 into the air over Marietta. The flight lasted just over 90 minutes. No major problems were reported. A legend had taken its first breath, but testing soon revealed a serious flaw. The aircraft was heavier than promised, and its wings were under more stress than engineers expected. Cracks began appearing in the wing structure. It was a warning sign of years of costly repairs still to come. By 1969, cost overruns had spiraled past $1 billion, the first program in history to blow through that number. Congress launched an investigation. Lockheed's finances were pushed to the brink. The Galaxy nearly became a cautionary tale before it ever entered service. Testing finally concluded in December 1969. In June 1970, the first operational Galaxy entered service with the United States Air Force. Once in service, the Galaxy became the backbone of American strategic airlift, hauling tanks, helicopters, and entire field hospitals across oceans. During the Vietnam War, Galaxies ferried critical supplies into forward bases, shortening a logistics chain that once took weeks. In 1973, during the Yom Kippur War, Galaxies flew an emergency airlift of American weapons to Israel, arriving faster than anyone thought possible. In the decades that followed, Galaxy supported operations in the Gulf War, the Balkans, and Afghanistan, along with countless humanitarian relief missions. Upgraded engines and avionics turned the aircraft into the C-5M Super Galaxy, extending its service life deep into the 21st century. More than half a century after its first flight, the Galaxy is still flying, a living monument to a design born of compromise and crisis. The C-5 Galaxy proved that air power wasn't only about fighters and bombers. It was about the ability to move an army anywhere on Earth. It reshaped how the United States projected power, turning strategic airlift into a weapon as decisive as any missile. And yet, buried in the archives, the flying wing alternative never entirely disappeared. It resurfaced decades later in a very different aircraft. The question that has fascinated engineers and historians ever since is simple. What if that shape had been chosen for the Galaxy instead? Everything you have heard until now is real history. What comes next is not. This is where we leave the historical record behind. Imagine that in 1965, the Air Force's Evaluation Board had judged differently, favoring aerodynamic efficiency over cargo bay simplicity. In this alternate timeline, Lockheed's flying wing proposal, codenamed here as the CX-4, wins the CX-HLS contract. Instead of a fuselage tube, the entire aircraft becomes one continuous lifting surface, with cargo carried inside thickened wing roots. This is where history ends and engineering speculation begins. The first challenge would have been cargo loading. A flying wing has no long, straight tube for drive on vehicles. Engineers would likely have needed a split cargo bay, carried in twin pods along the wing roots, complicating loading and centering weight. Stability would have been another obstacle. Flying wings are naturally less stable in pitch and yaw than a conventional tail-equipped design. In the 1960s, before digital fly-by-wire computers existed, keeping a tailless giant steady in flight would have demanded constant pilot correction. Northrop had already learned this lesson painfully with the EB-49 bomber, which suffered fatal instability accidents in the late 1940s. A 1960s flying wing Galaxy would have inherited that same fight against instability, only now scaled up to a much heavier airframe. Engineers might have compensated with small vertical fins at the wingtips or oversized elevons blended into the trailing edge. These fixes would have added weight and drag, eating into the very efficiency gains the flying wing promised in the first place. Ground handling would have posed its own puzzle. Loading ramps, maintenance access, and even simple things like boarding stairs need rethinking on a wing-shaped hull. And engine placement would have been contentious. Buried in the wing root for aerodynamic cleanliness, but a maintenance nightmare for ground crews. Despite the challenges, the payoff could have been real. Flying wings carry the potential for far lower drag than a tube underwing design. Lower drag could have meant longer range or heavier payloads without needing larger engines than the real Galaxy already used. But in the harsh political climate of the C-5 program, already drowning in cost overruns, a riskier airframe might never have survived Congress. A flying wing Galaxy could easily have become an even bigger financial disaster than the real aircraft ever was. Today, the instability problems that doomed early flying wings have largely been solved by computers, not pilots. Fly-by-wire systems make thousands of tiny corrections every second, something no 1960s autopilot could have dreamed of doing. This is precisely why the B-2 Spirit, and later the B-21 Raider, could embrace the flying wing shape that the Galaxy's era rejected. Modern composite materials also solve another old problem. The wing root strength needed to carry heavy cargo without a reinforcing fuselage tube. Some modern concept studies for future heavy-lift military transports have quietly revisited blended wing body shapes for exactly these reasons. NASA and Boeing have both tested blended wing body demonstrators, chasing the same drag reduction the flying wing Galaxy might have offered decades earlier. Yet even today, no operational heavy military transport uses a true flying wing shape. Cargo loading remains the unsolved problem. The tube and wing shape may be aerodynamically old-fashioned, but it remains unmatched for loading tanks, helicopters, and bulky outsized cargo. So would a flying wing Galaxy have succeeded? The instability problems, the cargo loading complications, and the immense political risk would likely have sunk the program before it ever reached the runway. The real Galaxy, for all its flaws and cost overruns, succeeded precisely because it played it safe with a proven shape. But the flying wing dream never truly died. It simply waited for the technology to catch up, and it found its home in stealth bombers instead. The C-5 Galaxy we know today is a monument to pragmatic engineering, built not for elegance, but for the brutal job of hauling war machines across the world. Somewhere in an archive in Georgia, a forgotten sketch of a wing-shaped giant still waits, a reminder that history is built from roads not taken. The galaxy that flew was not the only galaxy that could have flown, and perhaps that is the most human